Hello students, welcome to lecture 13. In this session you will be discussing about gate characteristic of an SCR or thyristor. So gate characteristic means as we had discussed in the previous sessions, we are aware that the SCR is mainly controlled by the gate terminal, right? So mainly to turn on the SCR, the control signal is given to gate terminal, that is gate voltage or gate current is the one which will be triggering the SCR into conduction mode, right? So gate characteristics in fact will give us the specifications of what should be the level of voltage or the current that will be coming at the gate terminal, and what will be the minimum or the maximum current that will be acceptable at the gate terminal. So all these specifications, in fact the design specifications pertaining to this gate characteristics will be provided by the manufacturer. So we will first understand what its characteristics are, all right? So in order to do that, we will consider this simple circuit. So you have this SCR, a 4-layer semiconductor device, PN, okay? To anode and cathode, you can imagine you have put that in a forward blocking mode, okay? You understand what it means now. So when you are subjected the terminals anode and cathode to forward blocking mode, okay, then if you give any control signal at this gate terminal, here is the gate terminal, okay, using this gate driving circuit, then you can make the SCR turn on. Yes, so you're aware of all these points from the previous sessions. See, observe here, we have these anode and cathode terminals. So the junction J1, J2 and J3. This is the junction J1, J2 and J3. Okay. Now, if I am applying some voltage to this gate terminal, all right. So there will be some current flowing through this gate terminal, right? So now if you observe the typical terminals gate and cathode only. So just for a sake, now you forget about anode terminal. If you are looking at only terminals gate and cathode, so you are applying voltage across gate and cathode, right? So if you look at this, then you see that it is this device is simply resembling a PN junction, right? So we know that the PN junction characteristics, we are aware about that. It would look something like this, right? So you're applying some forward voltage and you're looking at the current that would be flowing in the PN junction, and we know about its characteristics, right? So this characteristics say if my layer, the PN junction, if it is highly doped, if these two regions, P and N regions, if they are highly doped, then how would be the characteristics? If they are highly doped means what? There are a very large number of charge carriers and the conduction would be fast, isn't it? Conduction would be fast means the applied voltage would be very less, yes, and the current would be going high in a short period of time. So you may get the curve somewhere here for highly doped condition, isn't it? Follow my arrow. For a highly doped condition, the voltage applied would be very less, okay, and current would rise instantaneously, isn't it? What about lightly doped condition? If my P and N regions are lightly doped, okay, that means where there are very less number of charge carriers here, which means that the characteristics would be somewhat, it would be like this. That means in order to make current flow, you have to apply more voltage and the curve would resemble somewhere here. Okay, I hope you're getting. So the two curves, what I'm talking about, say the curve what I'm placing now here in this position where my mouse is moving, so that would be the curve representing the lightly doped condition, And if you follow my mouse here, so for highly doped condition, the curve would come somewhere here. So this is typical characteristics, right? So if I'm taking or representing the same with voltage versus current, okay, so as it is depicted in the textbooks, and that is how popularly the VI characteristics would be represented. If I'm taking V in y-axis and I in the x-axis. So here in terms of gate drive circuit, my V would be VG because it is a voltage applied at the gate terminal. So V would be in the y-axis, and I will call it as a gate current, IG. Okay, so my curve would look something like this. I hope you're with me. So in x-axis is my gate current and y-axis is my gate voltage. Okay, and this curve would be the one, the curve 1 would be the one which would be representing highly doped condition. Okay, and curve 2 would be the one which would be for lightly doped condition. Okay, I hope you are observing that. Okay, now so there are different points there. So at curve 2, this would be the maximum voltage. Okay, VGM. So this we will call it as VGM. VGM is nothing but the maximum gate voltage that can be applied. Okay, similarly here, so this point can be the maximum gate current. All right. So all these specifications at the time of manufacturing, each SCR or the thyristor is specified with this maximum gate voltage limit and the maximum gate current limit. Okay, and also the maximum average power dissipation limit also. So which is given by this hyperbola. Okay, wherein power dissipation limit or power dissipation average, which is nothing but the product of Vg and Ig, which is a constant, right? So the constant, so you will get a hyperbola like this. So these values, that is maximum average gate power dissipation, will also be represented by the manufacturer. That is what should be the limit, which should not cross or damage the device. That's the meaning. Okay, and there will be also some minimum voltage and minimum current ratings that would be specified by the manufacturer. All right, so VG minimum and IG minimum also will be specified. So what are all these? Say curve 1 here, curve 1 represents the lowest voltage values that must be applied. That is the meaning. Okay, and curve 2 represents the highest or the maximum voltage that can be safely applied to the SCR, so that you will avoid any damage to the device. Okay, so this minimum I will call it as VNG. It is nothing but a gate non-triggering voltage. Okay, gate non-triggering voltage. This also will be specified by the manufacturer. Okay, what does it mean? Gate non-triggering voltage means what? Say till this voltage range, a minimum voltage that can be applied in the circuit, but that will not trigger the SCR on. Okay, this is gate non-triggering voltage. That means sometimes in the circuits there will be some noise, there will be some unwanted signals, there will be some spikes. Okay, so even that, if those noise or the unwanted signals, if they are falling within this range, then it is acceptable, so that it will not trigger the SCR. Okay, so the care should be taken looking at the SCR, what SCR you have taken, looking at its specifications mentioned by the manufacturer, then your circuit should be designed in such a way. So even if you have a noise or any unwanted signal, with some minimum voltage, that will not turn on the device. That's the meaning. Okay. So all these specifications, if we uh, look at, it is nothing but with respect to gate terminal, right? So that's why we call it as gate characteristics. So what do you understand now? This region, the region what I'm showing now, following my mouse. So this would be the region which would be a safe region for the SCR to be used in any application, right? So the voltage what you apply should be more than this, okay, starting from this minimum voltage, and the voltage should not cross this range, right? And the current, the gate current also should be within this value. So then we say that the SCR what we are using, it is in the safe region. So in order, if you recall the diode PN junction characteristics what we had learned in second sem, okay, there again whenever you are using any device, you will look for a safe operating point, right? So how do you get the operating point, safe operating point from these characteristics? You will always draw a load line. Remember, you have to draw the load line. So wherever the load line crosses these characteristics, then we say that that point will be the point that is the safest point where you can use your device, right? So in order to draw the load line, say we will consider this circuit, the gate drive circuit. You have the gate source, which we'll call it as ES. You have a series resistance that is connected to the gate terminal, which we call it as RS. Okay, and you have applied voltage across gate and cathode, which we call it as VG, and there is a current flowing at the gate terminal, which we call it as IG. Okay, so from this, if you apply Kirchhoff voltage law, okay, we will get a equation ES is equal to VG plus IG into RS, right? So to get the characteristic, that is to get the two coordinates that we have to plot in this graph, we have to use this equation I said, okay? You have X parameter and Y parameter in the equation, right? That is X coordinates and Y coordinates. Which is your Y coordinate? That is VG. And X coordinate is your IG, right? So to get the two coordinates on these to draw the load line, you have to get two coordinates. So what you will do, you will make the coordinates, the parameters equal to 0, equated to 0, and find the other, isn't it? That's the way. So how do we do? Say if you make Y parameter equated to 0, then you will find the X parameter, okay? Equate the X parameter to 0, equate it to 0, and find the Y coordinate, okay? So doing so, if I make Y, that is VG is equal to 0, if I take VG is equal to 0, then according to this equation, I get IG is equal to ES by RS. So I'll call it as D, okay? So this is my coordinate what I'll get on the x-axis, isn't it? Because obviously VG is 0 means you will get the point on the x-axis, right? So when I make IG is equal to 0, okay, where will my point fall? The coordinate will fall on the y-axis, right? Obviously, IG is 0, that means the coordinate will be on the x-axis. So what would be the value in this equation? If IG is equal to 0, VG will be equal to ES. So that I will call it as point A, okay? So when I plot it, or coordinates A and D, I have pointed it on the x-axis and the y-axis. See, my D is here, which is my IG point, which is the value equal to ES by RS, and my VG is equal to ES somewhere here, okay? Obviously, the apply source will be always greater than the voltage VG, right? So it will be somewhere here. So my points A and B are located here on the coordinates. I've got the load line. So when I draw the load line, if you observe, it is cutting the curve 1 and 2 at S1 and S2, isn't it? So any point in between S1 and S2 would be the safe operating point. I hope you are understanding. Okay. So now say according to the particular device SCR what I'm using, if its characteristics, if its gate characteristics fall somewhere here, okay, I have a SCR and its gate characteristics curve, it is showing like this. So it is cutting the load line at this point. Okay, so that would be the safe operating point. So which means that the voltage applied to the SCR, okay, the particular SCR what I'm talking about, its voltage should be of this value and with the current would be of particular value here. That's a meaning. That's a meaning. All right. So that is nothing but the gate characteristics. All right. Let us pause now and solve this. You have a circuit here. A 220 ohm resistor is connected in series with the gate of an SCR as shown in figure. Okay, 220 ohms. The gate current required to fire the SCR is 7 milliamps. The gate current. All right. So what is the input voltage V in is the question. Okay. Just think, if you recall the expression, what would be the minimum, what is the input voltage V in is the question. So how do you write? Can you just pause and think? What should be the expression? So according to the Kirchhoff law, my expression would be V in is equal to IGR plus Vg, isn't it? Okay. Now, if you recall, to turn on this, the voltage applied, minimum voltage applied to this PN junction, that is across gate and cathode, would be 0.7. If you recall, 0.7 according to the silicon type of PN junction, right? So substituting that, all right, so you will have V in, so VGK, that is the voltage applied across gate and cathode, if you take it as 0.7, minimum 0.7, so IG is given there already, 7 milliamps, and your resistance value is given, so your applied input voltage should be 2.24 volts, all right. Okay. So, okay. So typically this is the gate characteristics of an SCR or a thyristor. I hope it resembles the previous circuit or the, I mean, not circuit, the picture or the graph what we had, the characteristic graph what we had. So as I mentioned, the manufacturer will specify all these ranges, that is the maximum gate voltage, okay, that can be applied, all right, the maximum current, gate current that can be applied to the gate terminal, the minimum gate voltage and the minimum gate current, and minimum gate non-triggering voltage will also be specified. So this is the range, that is OA range, OAG range is the voltage and the current here. So wherein the any unwanted signal or the noise signals voltage ranges can fall, okay, which will not trigger the SCR, okay. So whenever we are using the SCR, we have to look at the gate characteristics. So we have to see what should be the minimum gate voltage that can be applied. So only after this, the SCR would be turning on or triggering. I hope you are understanding now. So this should be the maximum gate voltage that can be applied. So if you observe the gate characteristics, you have three regions of importance. First is your OA region, so as I mentioned. So this is the region which sets limit on the maximum false signals that can be tolerated in the gate firing circuit. Okay, the meaning of that is, which is nothing but any unwanted signal or the noise signal should be below that VNG range or in this range, VA range. Okay. Second region is nothing but the OL and OV, or the minimum gate voltage and the gate current. So here it is it is not OL, it is OB and OG. Okay, so minimum gate voltage and minimum gate current. And the third is your the maximum range, that is OC, okay, and OF here, the maximum voltage range and the current range. So if you observe the safe region where you can use your from the figure, it is clear that the safety operating area of the SCR is B, C, D, E, F, G, H and B, closing it. Okay, so this area where any values, the voltage and the current values, if it is falling within this area, then it is the safety operating area of the SCR. All right. So generally, as I mentioned, the manufacturer will provide all these specifications, and looking at the specifications, if the curve it is falling within this typical characteristic, that is S1 and S2. Say I am using one particular SCR with the curve 3 and its curve is cutting the load line at S. So this is the safest operating point of the particular SCR what I am talking about. All right. So the gradient of the load line will give the required gate source resistance value as well. Okay. So if you observe that the gradient AD, okay, it will give you the value of the resistance, which is nothing but OA by OD. The slope what you are getting, OA by OD. All right. So that will give you the typical or the resistance, gate source resistance value RG, that can be used for particular operating point, All right. Okay. Now the SCR has a breakover voltage of 400 volts, a trigger current of 10 milliamps and a holding current of 10 milliamps, right? What do you infer from it? Think about it. What do you infer from it? And what will happen if gate current is made 15 milliamps? Pause a little bit and understand. The question is, there is an SCR, okay? Its breakover voltage is given as 400 volts, okay? The triggering current is 10 milliamps. The holding current is 10 milliamps. What do you understand with these? As I mentioned, all these specifications will be given by the manufacturer. See, a manufacturer has given particular SCR, its breakover voltage is 400, it is given. The trigger current is specified and its holding current is also specified. What do you understand with this? Okay, let me give the answer. So, the breakover voltage is 400 volts means what? Any voltage, that the supply voltage, what you are applying, the supply voltage with the gate open, okay? If the supply voltage is less than this breakover voltage, then SCR will not conduct, isn't it? It remains open. That's the meaning. Okay. So when the gate is open, when you have not applied any gate voltage, okay, and if the supply voltage is equal to this 400 volts, then what happens? SCR will close or it will start conducting. Remember, breakover voltage, okay. So breakover voltage is the voltage at which the SCR will shift to from forward blocking mode to conduction mode. Okay, that means conduction mode means what? It is conducting, current is flowing there. All right, that's the meaning. So I'll repeat, if the supply voltage is less than 400 volts, SCR will remain open, that means it does not conduct. If the applied voltage or the supply voltage is equal to 400 volts, then SCR will turn on, that's the meaning, or it is closed. So if you have to use these terminologies because most of the times SCR will be used in the application of switching as a switching or as a switch. Okay. Okay. Observe this. Trigger current is of 10 milliamps. What do you understand? Trigger current is 10 milliamps means what? Trigger current means what? The current what you are applying at the gate terminal, isn't it? So the gate current given is 10 milliamps. That means the gate terminal current what you are applying is, if it is 10 milliamps, okay, and if the supply voltage is less than 400 volts, then again the SCR will turn on. Remember the characteristics. Even though if the apply voltage, even though if it is less than this breakover voltage, but you can make this SCR turn on. How? By giving some control signal at the gate terminal, isn't it? So if my gate current is 10 milliamps as specified by the manufacturer, that means this is the minimum gate current required to turn on the SCR. That's the meaning. So if my gate current is 10 milliamps, then immediately the SCR will conduct. That's the meaning. I hope it is understood. Then next, holding current value is also given 10 milliamps. What does it mean? Now you have already triggered, the SCR is in conduction. Okay. Now if my gate current, if it is below this 10 milliamps, that means if my the anode current, the SCR current, anode current, if it falls below this 10 milliamps, that anode current, if it goes below this 10 milliamps, then the SCR will turn off. Remember, what is the definition of the holding current? Holding current is nothing but the maximum current of the anode current at which the SCR will remain in conduction mode, or in other words, if the anode current falls below the holding current, then the SCR will turn off. Remember, that's the meaning. So if the anode current in the circuit, if it is made to decrease, how do you do that? By withdrawing the voltage applied to the gate terminal. Okay, or if you are using a circuitry where you are reducing the voltage applied at the gate terminal, then obviously the gate current will decrease and obviously the anode current also will start decreasing. So if this anode current, if it is below this 10 milliamps, then SCR will turn off. Otherwise, SCR will remain in the conduction mode. Okay, you have to understand all these terminologies. Okay. Now the third point is, if gate current is increased to 15, initially it was 10 milliamps. If it is increased to 15 milliamps, what happens? Recall the characteristics again. If my gate current is increased to 15 milliamps, that means what? You are turning on the SCR earlier with still lower supply voltage. Recall that. Okay, that means if I increase the gate current, I can turn on the SCR earlier or faster, isn't it? Okay, so the conduction, that is the thyristor, can be controlled. That is, the way you turn on, at what time you turn on, can be controlled by this gate signal. All right. So if you are increasing, you are able to turn on the device faster or earlier or with the lower supply voltage itself. So lesser is the time needed to inject the charges if you are increasing the gate current. That's the meaning. All right. Now what happens? So the turning on of the SCR can be reduced with the higher gate current is what we understood. So imagine if my gate signals are say square pulse. All right. So if my width of the pulses, if it is wider, that means there is more gate current. All right. It is nothing but pulse width modulation, what we are talking about. So if I have to increase the magnitude of the gate current, say I have to increase the width of the pulse. Say for example, the pulse width here, if it is T, then the T should be greater than T on. What is this T on? It is the time required to turn on the device. Recall the switching characteristics. Okay. So to make the device turn on faster, or if you want to turn on the device earlier, faster, sooner, then the width of the pulse should be wider. This T should be more. The magnitude of this T should be higher. That's the meaning. All right. So based on that, if we know the frequency of the firing, that is if it is F, then from this you can get the relation for the gate power dissipation as well. So maximum gate power dissipation, which is nothing but the product of VG and IG, all right, it can also be written as PG average, all right, gate power, that is average gate power divided by FT, where F is my frequency of firing, okay, where T1 is the time period, all right, time period here, all right, and T is the width of the pulse width in second, all right. So this is again a relation. So with this, I hope you are copying down all the parameters and equations. With this, I expect you to go through this problem and try to solve. Um, it is very simple based on all the explanation what you have gone through in this session. So you should be able to come out with the parameters what is asked. So what is asked? Calculate the resistance. So to find the resistance, for the gate drive circuit, you apply the Kirchhoff law. From the Kirchhoff law, what you have, try to see what are the parameters you have there, and try to find out the unknown parameters from the given parameters. I'm giving you all hints here. All right. And finally, calculate the gate power dissipation. Just now you have recalled uh, the the expression what we discussed. All right. So go through this and try to answer this question. All right. We will discuss about this in the next session. All right. See you in the next session.